Okay, this is objective 10.1a, and today's topic is solving trig equations. Today, the basics. And we will not finish this note page today. We'll finish it tomorrow, so your assignment will happen tomorrow during class. Your essential question is this: how do I use my knowledge of special right triangles plotted on the unit circle to solve trig equations for angles x or theta, and I should write, oh, I erased all that. Unit circle to solve, for angles x, theta, and so on over given intervals or infinite. Domain. So basically, over a period of 2 pi or over a period of 4 pi or over infinity, negative infinity to infinity. Okay, so we are going, and that should be a question. How do I use my knowledge of the special right triangles plotted on the unit circle to solve for angles x, theta, beta, gamma, whatever, over given intervals or infinite domains? All right, so how to find solutions. First of all, you want to solve the equation for sine of x equals some number or cosine of theta equals some number. You want to get the equation manipulated so that it's in that format. When it's a simple one and you don't have multiple trig expressions in the same equation, we'll get there. And then step 2, you find, well, what was the word I used here? I want to use the same word I used before. Sorry, give me a sec. Values, that was the word I wanted to use, of x or theta or whatever that satisfy the equation. Okay, now when we're in algebra, what we're doing is we're solving for x, right? Yes. We're solving for that missing piece of information. We'll solve for x or we'll solve for a or whatever. Sometimes we'll get one solution, sometimes we'll get multiple solutions. In this case, when we're solving trig equations, what we're solving for, hear my words, we're solving for the angle measure. What angle measure makes this true? What theta makes this true? Is it pi over 6? 5 pi over 6? What is it? So algebra and trig together. You are solving for the missing angle measures. That's what you're looking for. All right, here's the rule. If degree measure is not specified, then the solutions of the trig equation should be expressed in radian measure or as a real number, because that's radians. No, that's the symbol for the set of real numbers. Today I'm going to introduce to you another, and you may already know this, off down here on the side, we'll do it down here in the guided example. I'm also going to introduce to you the set of integers. So if you draw a number 7 and then you draw an upside down 7, it's a weird looking Z. This is the set of integers. So what I'm going to do is just going to actually give you an example. The set of all integers, real numbers, that's everything. Pi, square root of 2, all the numbers. Okay, rational and irrational. The integers are the positive and negative whole numbers. So you will see me use that Z. We're going to start writing things in calculus notation. This is the set of integers. So you could write the set of integers. That's what that Z represents. Okay, so let's start adjusting to that notation. All right, so let's talk about, you remember that in the objective I said we were using our knowledge of the special right triangles plotted on the unit circle. And so my pictures did not come up very well, so I'm going to fix this up real quick. All right, that is terrible. Okay, over here. This is an example of the 30, 60, 90 right triangle, where the relationship between the corresponding sides are the short side is x, the long side is x times the square root of 3, and the hypotenuse is 2x. If you haven't memorized that by now, you really need to. And what I did was I took this triangle here on the unit circle in standard position, reference triangle, quadrant 1, and I brought it out, and I'm going to double its side. So you know in the unit circle, the hypotenuse is always, what's the length of the hypotenuse on the unit circle? 1, right? It's 1. I'm going to double it, so the hypotenuse is 2. So I'm going to put my 30-degree angle down here. Okay, so this is a representative of the 30, 60, 90, where the reference angle is the 30-degree angle. And the opposite of that would be half the hypotenuse. The short leg is half the hypotenuse, so that's 1. And then the long leg is 1 times the square root of 3, so it's the square root of 3. So I'm just doubling the size of the triangle because that makes it a little bit easier when I'm writing my ratios. Because you remember that the sine is opposite over hypotenuse, right? And the sine of 30 degrees is 1 over 2. Truth. So in this case, theta's reference is sine. Remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent's opposite over adjacent. And then, of course, you got your reciprocal functions. So sine is opposite over hypotenuse, 1 over 2. Cosecant, flip it over, 2. All right, so on the 30, 60, 90, this is true statement. Cosine is adjacent over hypotenuse. So that's the square root of 3 over 2. Now secant is the reciprocal of that. But over here, just this one time, I'm going to show you why the answer is going to be what it is, but it's not going to be the first form of this answer. So if we do secant, we're doing the square root 2 over the square root of 3. But typically, we rationalize the denominator. So in order to do that, I would multiply times the square root of 3 over the square root of 3. Truth? Yes. So that gives me 2 times the square root of 3 over 3. So secant, simplified and rationalized in the denominator, is 2 square root of 3 over 3. And typically, we'll see our answers in that format, so that's useful. Tangent is opposite over adjacent. That's 1 over the square root of 3, or simplified the square root of 3. I'm doing the math for you already. Cotangent is the square root of 3 over 3. Okay, so if I go up here to my unit circle, I know in quadrant 1, everybody's positive. I'm going to switch colors. So everybody's positive in quadrant 1. And in quadrant 1, this is the 30-degree angle, or it is pi over 6 radians in quadrant 1. In quadrant 2, where sine is positive, I'm going to drop in the vertical line, terminal side to x-axis, so you can see the reference triangle. And this is 150 degrees, or 5 pi over 6. And I know it's kind of hard to do that on your triangle. Your little pictures are pretty small, so just make it fit. We'll go down to quadrant 3 here, drop in another vertical line. So now we're in the quadrant where tangent is positive, and we are at 210 degrees, or 7 pi over 6. And then we'll go over here and do the last special right triangle of the 30-degree angle, which would be at 330 degrees. Check my math. Or 11 pi over 6. So you can see all 4 of those triangles in the quadrants, and this is the quadrant where cosine is positive. Okay? So useful information. Now on the test, if you can do this, you're good to go. Now, if you have your exact value sheet all filled out and you want to use it on the test, fine. Capping your grade at an 85%, and I don't have a problem with that. I don't, just so you know. All right, what I want to do before I go and do the 45, 45, 90, which I put here in the middle, is I'm going to come over here and do the 60-degree angle where I'm pulling that triangle out. Okay. And the hypotenuse is still 2. The short side down here is 1, but now it's the adjacent to the 60 degrees instead of the 30 degrees. And so the opposite will be the square root of 3. So you can see it's the same triangle, right, as the 30, 60, 90, but now my reference angle is 60 degrees instead of 30 degrees. So the opposite and the adjacent switch places, which means the sine and the cosine switch, they're cofunctions. 30 and 60 degrees, complementary angles. Okay, so if I come down here to sine of theta, 60 degrees, that's the square root of 3 over 2, opposite over adjacent. Cosine's 1 over 2. Truth? Tangent is opposite over adjacent. Square root of 3 over 1 is the square root of 3. And so I can just use this reference over here for cosecant, secant, cotangent. So this would be 2 square root of 3 over 3 for cosecant. Secant would be 2, and cotangent would be the square root of 3 over 3. So up here on your unit circle, here's your 60-degree angle, or your pi over 3, right? 60-degree angles, just take pi, divided in by 3, you'll get 60 degrees, true? Right? Where everybody's positive. Where sine is positive in quadrant 2, this is 120 degrees, or 2 pi over 3. Tangent down here, this would be 240 degrees, or 4 pi over 3. Right? Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. And then over here, this would be 5 pi over 3, or 300 degrees. And then, of course, if you wanted to draw in those vertical lines so you can see the reference triangle plotted on your unit circle, you can do that. Questions? So that's the 30, 60, 90 turned on its side. It's the same information. It's just switching the focus from 30 degrees to 60 degrees. Let's go do this one. This one's going to be the 45, 45, 90. So I'm going to pull that picture out and put the reference angle down here in the corner between the x-axis and the terminal side at the origin. This will be my opposite. This will be my adjacent. This will be my hypotenuse. My hypotenuse, remember, I'm doubling it to 2. So my opposite side will be the square root of 2. My adjacent side will be the square root of 2. It's good to memorize that specific special right triangle. And then I forgot to mention this up here. For the corresponding sides of your 45, 45, 90, your legs are the same. They're both x, whatever the measure is. And your hypotenuse is x square root of 2. Man, my pen is not cooperating. How many times a day do I say that?
Not many.
It's erasing everything. The picture is ridiculous. Okay, my iPad I like so much better because it makes straight lines. Okay, so here in quadrant 1, this is 45 degrees, or pi divided by 4. In quadrant 2, where sine is positive, this is 135 degrees, or 3 pi over 4. In quadrant 3, where tangent is positive, this is 225 degrees, or 5 pi over 4. And in quadrant 4, where cosine is positive, this is 315 degrees, or 7 pi over 4. Sorry about the mess. That just does not look pretty. I hope it's a lot prettier on your note page. Excuse me. Okay. So, ready? Do you need a little more time? Okay. Such a mess, such a mess. So what do we know about sine of theta? Sine of 45 degrees is opposite over hypotenuse. Square root of 2 over 2. You should recognize that from the unit circle. The sine of 45 degrees is the square root of 2 over 2. Cosecant will be the square root of 2. Cosine is also the square root of 2 over 2 because the legs are the same length, and your secant is the square root of 2. Tangent is just sine divided by cosine. So what do I get when I divide sine by cosine? 1. And the cotangent is the reciprocal, which is also 1. So the 45, 45, 90 is nice because it's easy to memorize those values. Okay? All right. So now, what we just have to be thinking about is, like, for example, if I say the cosine of theta is negative square root of 2 over 2, what special right triangle does that make you think of? If I say the cosine of theta is equal to negative square root of 2 over 2, what triangle? 45, 45, 90. So I just want to know, where is cosine negative? Quadrant 2 and 3. So I'm thinking about the triangles that are 45 degrees in quadrant 2 and 3. That's what I'm thinking about. Question. Did I get it backwards? Oh, let's fix that. You are right. Fix these. Sorry. Erase. Yeah. No, square root of 3 tangent. Sorry, tangent of 30 is 1 over the square root of 3, which is the square root of 3 over 3. Cotangent is the square root of 3, because that's adjacent over hypotenuse. So this would be the square root of 3. Thank you. That would be really false information for you to have out there. So switch those. Thank you. I don't know how I did that wrong after 4 of their lessons today doing it right. There you go. It's because I'm not looking at my notes anymore. Okay. So, like I said, if I were to say cosine of theta is negative square root of 2 over 2, that should make you think of a 45-degree angle, and you just want to know where is cosine negative, quadrant 2 and 3, like that. So let's do a couple practices. The example says, find solutions of sine of theta equals a half if A, theta is in the interval 0 to 2 pi, so that's just a short interval, or if theta is any real number, which means the full domain, negative infinity to infinity, any number. So it is indicating to me that I'm looking for theta in radians or degrees. Radians, because radians are real numbers. Degrees are some human constructed measure of an angle. Okay. All right. So what I think of is this. The instructions say step 1, make sure the equation is solved for sine of theta equals a number. It already says that, right? Sine of theta equals a number. Okay, step 1's done. So now what we're trying to do is find out what does theta equal. That's what we have to solve for. What angle makes this a true statement? So I think first, sine of theta is positive 1/2. Positive 1/2. Sine is positive in quadrants 1 and 2. So it's the first thing I think of. And so I will quickly just sketch out quadrant 1 and 2. Where is sine 1/2? Now, a lot of times I'll get out my little left hand. I'm drawing a really ugly left hand right here. And I'll think, I remember that your top fingers are your cosine and your bottom fingers are your sine, right? And I want sine is 1/2. So that means I'm going to bend this finger in, which is at 30 degrees, right? Truth? That would give me sine 1/2. So I'm always using my beautiful little left hand here. So that would be a 30-degree angle, but in radians, that would be pi over 6, right? And that would be quadrant 1. Sine is positive. Over here in quadrant 2, I want that same 30-degree angle right here. That would be 5 pi over 6. So in one full revolution around the unit circle, sine equals 1/2, and I know it's 1/2 because remember that's your second coordinate, cosine square root of 3 over 2, and over here, negative square root of 3 over 2, half, sine equals 1/2 in both of those measures. And so I could say theta equals pi over 6 and 5 pi over 6. And I could get out my calculator if I wanted, and I could plug in sine of pi over 6 and have the calculator go, yep, that's 0.5, check, good answer. Okay, another way I could do, you'll notice that I have this graph down here. And what I did with this graph, I'm going to zoom in here for a sec, is I'm going to explain to you what this illustration means. So it takes the equation, not y equals. We started out with the equation. This is really great when you're checking your work in Desmos or you're needing a little bit of a support until you're feeling more confident. What you can do in Desmos is you can, or your graphing calculator, take each side of this equation, so the left side and right side. So you would go y sub 1 equals the left side of the equation, and that's this blue graph right here. You can see the sine function just going every 2 pi. It's got a full wave up and a full wave down. There it is, the sine function. And then you do y sub 2 equals the right-hand side of the equation, half, and that's this horizontal line right here. And every time the two lines intersect, you're finding a solution that's true. I like it. And so you can see here in quadrant 1, your solution. And in quadrant 2, 5 pi over 6, your solution. You know, just make sure your settings in your x-axis are in units of pi over 4 or whatever you got to do so that you can look at it. And what's nice about Desmos, if you're using Desmos, is you can just click on the intersection and it'll tell you what the point is. Okay, so that's nice. But anyway, so that's a really cool way to check your work and know that you have the right answer. If you don't have your graphing calculator handy, you could use Desmos. Okay, but you'll notice that if I go over and the sine function, which is continuous and periodic, and it continues to go through this half over and over again, it also goes through half at 13 pi over 6. And 17 pi over 6, and over here somewhere, and over here somewhere. And if I go backwards at negative 7 pi over 6 and negative 11 pi over 6, it's going to consistently continue to pass through the sine of theta equals 1/2. So how would we write the answer to theta as any real number without writing all of them? Well, let's look at it. We know, I'm going to draw a picture. You don't have to draw this picture. That sine of theta is positive in quadrant 1, right? And sine of theta is half at pi over 6. So if I go all the way around, what do I add to pi over 6 to get back to that same right triangle? What's the distance between here and here in radians? 1 full revolution. 2 pi, right? And if I continue to multiply it times whatever integer I want, I can make my integer -1, which means I would rotate backwards. That would get me back to there, right? So every 2 pi, because remember the sine of theta is periodic over 2 pi, it'll repeat. And so we could say theta equals pi over 6 plus 2 pi times the integer, as long as n is an element of the set of integers. I can multiply 2 pi times -5, which means I just rotate backwards 5 times. I'll continually get back to quadrant 1 and that 30-degree measurement. Okay? Or in quadrant 2 at 5 pi over 6, so I'll come over here and erase my picture, and I'm just illustrating here so you can understand. 5 pi over 6, and I rotate around. I have to rotate 2 pi, right, to get back to quadrant 2. So I would multiply that times 2 pi times n. And so this would be my solution, and I might just make a note that as long as I define that n is an element of the set of integers, then I've written all the solutions. So remember, sine and cosine, secant, cosecant, periodic over 2 pi. You got to rotate 2 pi to get back to quadrant 1 or quadrant 2 or quadrant 4, whatever it is. Questions about that? I think so. All right. So here we go. Find all solutions. You try. Find all solutions for sine of alpha equals negative square root of 2 over 2. So my first question to you is this. What right triangle, special right triangle, does the sine equals the square root of 2 over 2 make you think about? 45, 45. Not your equilateral, because that's a 60, 60, 60, but an isosceles right triangle. Isosceles. Your 45, 45, 90. And where is sine negative? Quadrants 3 and 4. So you're talking about that angle and that angle. Okay, so I'm going to press pause. You can try it out, come back and try the second problem too, cosine of beta. All right, so there we go with your sine of alpha is negative square root of 2 over 2. That's in quadrant 3 and 4. And those are on the 5 pi over 4 angle and the 7 pi over 4 angle. So since sine is periodic over 2 pi, and you were looking for all solutions, you would add 2 pi times any integer, and then same thing with 7 pi over 4. Getting back to quadrant 4, you have to add 2 pi. For cosine of beta equals positive square root of 3 over 2. Cosine's positive in quadrant 1 and 4. And cosine is equal to the square root of 3 over 2 and at pi over 6. So it's that 30-degree angle down there, and then this 30-degree angle over here at 11 pi over 6. And then adding 2 pi times n. All right, we're going to do 2 more questions on the back, and then we'll be done for today because the bell's going to ring. So here we have find all solutions for tangent of gamma equals -1. So I want you to tell me what triangle, special right triangle, does that make you think of when the tangent, sine over cosine, is 1? 45, 45, 90. So I want you to tell me, when is tangent, what quadrant, where would these triangles lie if my tangent's -1? 2 and 4. So what I'm going to do is I'm just going to cut those two values in half. I don't know why I put arrows. I didn't need to. But anyways, here's something to note just for trivia. The tangent of gamma equals the slope of the line, -1. This is a slope, down 1 over 1, down 1 over 1, down 1 over 1. Tangents always slope. Okay, so that's quadrant 2 and quadrant 4. And it's a 45, 45, 90. So this would be 3 pi over 4. And then 7 pi over 4. And then the next, what could I do to get from here to here? What could I add? Pi, right? And then I could add pi again, and I could get from here to here. And then I could continually add pi, and I could get from quadrant 2 to quadrant 4 every time. Oh, then you know writing tangent is periodic over pi times n instead of 2 pi times n, because every pi you're back at a positive tangent, or every pi you're back at a negative tangent. So here's what I know. Gamma is equal to 3 pi over 4 plus pi times n, as long as I state that n is an element of the set of integers. I don't have to write, and it would be more than I need to do to write 7 pi over 4 plus pi over n. Because 3 pi over 4 plus pi over n, pi times 1, is 7 pi over 4. So with tangent, sometimes you only have to write one solution. Okay, you guys do this last one. Press pause on the video, do it by yourself, then come back and check to see how you did. And then we'll stop for today. Okay, so we found that tangent is positive in quadrants 1 and 3. And the tangent of theta was equal to the square root of 3 when theta equaled pi over 3 and 4 pi over 3. So our solution was pi over 3 plus pi times n, for n is any integer. Thank you. We'll finish tomorrow.